let's see if Ampere's law fits in with the loopiness of the magnetic field. So integral of B dot ds around an Amperian loop equals mu naught times the current enclosed in that loop. And now let's draw a current loop to make the magnetic field. So we've thought about current loops a little bit. So there is a current loop. That's a loop of wire sitting not quite in the plane of board, kind of tilted towards you. I don't really want to draw the current direction because I'm going to draw a lot of fields all around it. In fact, I'm going to get this out of our way. So for now, let's just think about this. So we calculated the B field here earlier, and we calculated how the B field goes down as you get farther away. But early in learning sequence 6, we talked about how really this is what makes magnetic fields, and it tends to make them stick up like that in the middle, but then they tend to go around like this. Right? And then it goes around like that. And we might have one up here like that. This is really the north and the south pole of a magnetic field. If you have a current loop, in this case, right-hand rule says it would be going around from the back to the front like that. B would go up, north pole, south pole. And this is really the fundamental unit of the source of magnetism as a current loop. Let's stick a bunch of Amperian loops on it and see if Ampere's law makes sense. Write it again. So let's stick it one place here. So now I'm going to have it go around and enclose a little bit of the wire loop. Okay, we have many loops here. So this is the current carrying wire loop. This is now my Amperian loop that is interconnected. All right, and let's just think about it. That's all we're doing here is we're just thinking about fields. The B field is kind of going around with that Amperian loop. So if we walk around it this way with our DS's, like that, you can see that DS and B are always going to be more or less in the same direction. Therefore, you're going to get a big whopping value here, right? Adding up a bunch of positive things all the way around the loop, get a big number. So for that one, does the current penetrate the Amperian loop here? And the answer is yes. It had to have come through the Amperian loop right there. So that one works. Let's draw an Amperian loop sitting up here, kind of like a halo on the wire loop, the halo being yet another loop. So there's the Amperian loop sitting above the wire current loop. What would its situation be? Well, let's look at the other side first. Now for this Amperian loop, the right-hand side is going to be 0 because no current goes through that Amperian loop, right? All the current's down here. The loop's got nothing going through it. So do we get 0? Well, let's think about this. Here, the DS is going into the board. Here, it's going along the back. Here, it's coming out of you. And then here, it's going that way. So you can imagine the DS doing that. What is the B field doing? The B field, in this case, it's always kind of like that, right? It's coming out like that. And here it's coming out of the board. And here it's going into the board. So in actually every case, the B field is perpendicular to DS. You really have to visualize it in 3 dimensions, but everywhere you go, DS is around the circle. Everywhere you go, B is shooting away from the circle. So it's at weird angles with respect to the plane of the board, but it's always at 90 degrees to the path. Okay, like that. So in that case, this side is also 0, which is good. B is perpendicular to DS. No current goes through the loop. Let's draw another loop. This one, let's draw it in the plane of the board. Here, like that. Now, the current loop is sort of sitting like this, but this one is flat right here. If we go around it, we can have a DS this way on that side, a DS this way. Here we could have a DS that way. Here we could have a DS that way as we go around. Let's think about this side. What would B dot DS be? Well, here the B is kind of going up. So B is along DS. So So we get a bunch of positive contributions to B dot ds. And then it goes sideways. They're perpendicular again at 0. But here, B is kind of against ds. Right? They're against each other. The dot product is negative. So you have some positive dot product on this side, some negative dot product on this side. They add up to 0. Right? So on this one, you'd get 0 here because it's nice and symmetric. Even if it were symmetric, the positives on one side, the negatives on the other side would cancel. And on the right-hand side, sure enough, there's no current going through that loop. Right? All the current's up here. The Amperian loop has no current going through it. So this was just some thinking and visualization to show you Ampere's law is always true. You'll always find anywhere you draw this loop. We could draw some crazy Amperian loop like this. And if you sit there and think about the direction of everything and the current, it'll always work.